ihr mich hört? Hört ihr mich? Good afternoon and welcome to the Quantum Future Awards 2022, coming to you live from the Alexander von Humboldt room at the Federal Ministry of Education and Research here in Berlin. A very warm welcome to everybody who is here in the room with us and of course to everybody who is joining us online. My name is Monica Jones. I'm a freelance journalist and news anchor at German International Broadcaster DW, and I have the great pleasure to guide you through this very exciting awards ceremony in which the Federal Ministry of Education and Research, which in short, and I'll stick to that from now on, is called the BMBF. It awards prizes for outstanding PhD and master theses in the field of quantum technologies. Why? Well, quantum technologies is really important for many reasons. First and foremost, because it has great potential for our future economy and society. And that is why already back in spring 2018, the BMBF launched the Quantum Future Program together with a quantum technology community. And the aim is to make progress of quantum technologies visible so that we know that it exists, which is very helpful to use them, but also to highlight career opportunities in the field of science and industry. And the Quantum Future Awards are part of that very program. Now, the award honors master's and PhD theses that have a clear application reference to quantum technologies. Now, there are quite a variety of applications possible, which is why natural sciences, engineering, information sciences all could be submitted. In today's final, the finalists will present their work in short pitches, 3 minutes each. And at this point, I would like to welcome a special welcome to the finalists who are in the room with us, sitting here right in front of me. And you know, you're all fantastic, you're all winners, simply because you're here already. And I do keep my fingers crossed for all of you, and I really look forward to those pitches later on. Good luck. Those who win can already look forward to what they will get, because the first and second place winners in both categories, that's the master's and the PhD, they will receive study trips worth 6,000 euros, that's for the winners, and 4,000 euros for the runner-ups, respectively. And the ministry also awards an audience prize, because scientific results, they should not only benefit society should ideally also know they exist and even better understand them. And this is where you come in, you, our online viewers, because during the live stream, you can vote online for the best and the most comprehensible pitch. As the main prize, the winner can expect a further training opportunity in the field of science communication. And of course, there's also a jury of experts who will determine the winners on the basis of the pitches now, but also on the previously submitted application documents. And this is a very good opportunity to thank the jury members. There are 3 of them representing industry, science and politics. And here on stage with me, I already have 2 representing industry and science. Our industry representative is Dr. Michael Marthaler. He's co-founder and CEO at HQS Quantum Simulations. And to get him to know a little bit better, because after all, he is one of those 3 people who's going to make a decision, maybe a life-changing decision. He received his PhD on QED in superconducting devices at the University of Karlsruhe, which is now known as KIT. As a researcher, he designed and taught lectures on quantum computing from 2010 to 2019. He led a research group working on quantum simulation, quantum metamaterials, and open quantum systems. And now, as CEO, he is the main representative of the company and responsible for its long-term vision. And it sounds like an awful lot of work. So he still found time to be a jury member and to be here with us today. Thank you so much for that. And there's another jury member who is also very busy and who also found the time to be here with us, Professor Dr. Christiane Koch. She is our jury member from the field of science, and she's a university professor for theoretical physics at the Freie Universität Berlin. Amongst her many activities, she is also associate editor for Science Advances and chair of the Quantum Optics Division of the German Physical Society. And there's much more. I had to just pick some of the highlights because we obviously want to be able to go on with the awards as well. But thank you so much to both of you for being here, for taking the time, and for looking and listening to those pitches as they come up. The third jury member, obviously still missing from the field of politics, also happens to be our host. So now I would like to give the floor to the Director General for Research for Technological Sovereignty and Innovation at the Federal Ministry of Education and Research, Professor Ina Schieferdecker.
Thanks a lot. Thanks for having me here. Good afternoon to everyone here in the room and those of you joining us online. And most importantly, of course, honored finalists, it's my great pleasure to welcome you all to the grand final and presentations of the Quantum Future Award. Following two virtual award ceremonies in the last 2 years, I'm really especially pleased that this year we are able to welcome the jury, our finalists and their guests here at the BMBF today in Berlin. All of you, our honored finalists, have decided to carry out research in the field of applied quantum technologies, and for very good reasons, as we learned before. We all know how incredibly important quantum technologies are for the future because they really have the chance to change our lives. Maybe your life's going to change today. One day, quantum computers will be able to solve problems that seem, as of now, being unsolvable. Quantum sensors will be able to take more precise measurements than ever before. Quantum communication will create a new standard of reliability and security for data transfer and information exchange. But we also all know that there's still a long way to go up until your ideas and all the ideas of others become reality in our societies. There are many scientific and technological questions to address and which need to be answered. That's why we need you here and you online, young scientists who are passionate about quantum physics, quantum math, quantum computer science, quantum engineering, and if I forgot one discipline, please forgive me, who use their knowledge, talent, and passion to develop quantum technologies that can be put to practical use, who want to change our society for the better. That's why we at the BMBF have been funding the next generation of quantum technology researchers for a number of years now. We see the huge demand for specialists in the field and hope to reach out to your generation in particular with this Quantum Future program. This program takes a variety of approaches. We have the Quantum Future academies, because it's already a series, which offers bachelor and master students the opportunity to spend a week in Germany to get insights about the German ecosystem on quantum technologies. This year, the Academy was attended by participants from 25 European countries. And next year, we will host this event together with our cooperation partner from Israel. The Quantum Future Junior Research Group give young academics the chance to lead their own research team, their own independent scientific group. A few weeks ago, our 18 young junior research groups were met currently and receive, so to say, their funding, and we saw all their impressive results so far. And then, of course, there's a Quantum Future Award, which is the reason why we are all here today. on screen and on site. It's already the 5th time, and I'm really looking forward the award ceremony and the presentations, your pitches. Your project stood out from all the many other applications you won already, as been said before. So you are winners already, no matter if you make it to be 1st or 2nd placed. Congratulations for making it here. So, and I thank you also for making your time coming here, for preparing the presentations, for giving the pitches, and we'll hope to get good insights from your pitches and from the networking that we can do here. You have exactly 3 minutes, just 3, and 1 single slide for your presentation. That's tough, we all know, but I guess you trained before, and we are very optimistic and rather sure that you're going to make it. So whenever I said we, I meant the whole BMF. It's just me that can give you the words here, but it's our great pleasure and honor to support people like you with the funding instruments that we create. And of course, I like to thank the jury members. It's hard work to read all the theses. Christiane Koch and Michael Marthaler, thank you for that, for being here, for taking the time in any way, tough schedules that you have. So, well, to make it short, I leave the floor to you for your pitches, and I hope that we all have an interesting, exciting, and also entertaining program. We hope to get new insights, and I wish you good luck, all success here and for your future scientific career, because we need you to make changes to this society, also with quantum technologies. Thank you for that already now.
Thank you so much, DG Schieferdecker. And as we both stressed it, of course, again, 3 minutes. And when we're talking about quantum technology, it's not exactly something that is not very complex, but we know that you will be able to manage and present your very, very specific, very complex, complicated, comprehensive project in 3 minutes to us. No doubt about that. So it's time now to meet our first finalists. We start with a master's category. 5 young scientists are now going to present their work in those very short pitches, one after the other, to convince the jury and you. So for our online audience, perhaps this piece of advice: as you're watching the pitches, do take down notes, because at the end of both rounds of pitches, we will not have a big review, which, like you would know from the Eurovision Song Contest or anything else, to jog your memory. You should take notes so you remember yourself. Of course, there is a list with names in your voting tool, which should help you, but do take down notes so it doesn't get lost. Are we ready? Okay, everybody's nodding. Then let's start with the first round of pitches. I'm going to briefly introduce our finalists, briefly say what the name of their thesis is, and then your 3 minutes start. Our first finalist is Robin Allert. He completed his master's degree at the Technische Universität Munich. His thesis is entitled Quantum Sensors in Diamonds for Lab-on-a-Chip Applications, and it is highly relevant for the field of quantum sensing. Robin, please come to the stage, and your 3 minutes will start as soon as the clock starts running.
Hi, I'm Robin. And I have to start my pitch with a small confession. Before switching to quantum science, I actually started studying chemistry, specifically chemistry for drug development. However, the first time I went into the lab and had to work with lab animals, I completely bailed. I couldn't kill lab animals for the sake of science. However, it made me wonder if there isn't a better solution. And yes, there is. So-called lab-on-a-chip devices. Basically, a whole biology lab shrunk down to the size of a credit card. Today, this technology can do already amazing stuff, like artificial organs, lungs, hearts, livers, for drug development. However, to really understand what's happening inside these chips, and specifically to do chemical analysis, we need much, much better sensors. So I went out and was looking for a solution, and I came across quantum sensing, a subfield of quantum technology where we use qubits as sensors. In essence, while quantum computation, for example, tries to isolate the qubits as much as possible from their environment to really lower the interactions, we embrace these interactions, allowing us to use qubits as ultra-sensitive sensors. And in my master thesis, we now combined these two technologies. For the first time ever, we created a microfluidic quantum sensing platform for lab-on-a-chip applications. And here you see one, and as well on the screen, just enlarged. As qubits, we use the nitrogen vacancy center in diamond, and just as a reference, that's the diamond. It's just a millimeter in size, and it's perfectly sized for lab-on-a-chip devices. These NV centers are great because they work at room temperature, a vital feature if we want to use quantum technology in biological systems. These centers allow us to use or to measure many different parameters, but most interestingly, they allow us to measure chemical or do chemical analysis. This basically, by just looking on how the superposition states of our NV centers evolve over time, we can do really deep chemical analysis. And together with our really adaptable platform, this allows us to do multiple applications for the lab-on-a-chip community, but also for the quantum sensing community. Thus, our platform is a truly unique and novel tool which allows us, for example, to do drug development without having to kill lab animals. Thank you.
Thank you. Thank you, Robin. Well within time. Thank you so much. That was our first pitch. Pitch number 2 now will be presented by our second finalist, Uday Chandra Shekhara. He completed his master's degree at Friedrich Schiller University, Jena. His thesis is entitled Polarization-Based Quantum Bit Error Rate Optimization for Quantum Communication. That's already a mouthful. And it is highly relevant for the field of quantum communication. So, Uday, we look forward to your pitch. And the 3 minutes start as soon as the clock's running.
Hello everyone. I hope everyone is aware that this time the Nobel Prize was awarded for spooky action at distance, as Einstein described it, which is also the so-called entanglement. My work is very close to this. I use entangled photons to establish secure communication and a transition from lab case scenario to the real-world application. I work with the polarization property of entangled photons. So there's a highly critical task which need to be addressed even before establishing the communication. Let's take a single photon and measure the polarization state. If the measurement frame of reference is aligned, then you have 100% certainty of measuring only one polarization. However, if the measurement frame of reference is not aligned, then you have a probability of measuring two different polarizations. This is a problem. Now let's go to entangled photons. When you distribute two entangled photons, one to Alice in a galaxy A and other one to Bob in a galaxy B, it is necessary their frame of reference is also aligned. For this purpose, we do polarization correction. And the best part of my thesis is we just use one polarization correction in front of one of the party and do the polarization correction. Both the photon changes the polarization. And this is highly impossible in case of classical communication. We know that polarization correction is critical. As a solution for that, we have developed a uniquely designed polarization correction module with a stack of waveplate arranged in a particular order. And further, we have developed a model-based algorithm in order to perform the automatic polarization correction. Below, you can see this polarization correction module was used on a 1.67 kilometer terrestrial free space quantum link, and irrespective of the time of the day, we are able to perform polarization correction and reduce the error factor less than the threshold requirement for establishing secure communication. And a noteworthy feature about this module is you can do daylight polarization correction and perform daylight quantum communication, which is still a milestone for many groups all over the world. And this module was also used in establishing the first quantum secured video conference between two German federal agencies at Bonn as a part of QNet project. As an outlook, I would like to tell that it takes just 3000 qubit quantum computer to break our current communication encryption. And we are not far from this. So we need secure communication, and this module can play a vital role in establishing a metropolitan quantum network and even to an extent of a global quantum network. Thank you everyone for your attention. See you.
Thank you very much, Uday Chandrasekhara. And the microphone is rescued. Thank you so much. Our third finalist in the master's category is Jesko Fleming. He completed his master's degree at Gottfried Wilhelm Leibniz University, Hannover. His thesis is entitled Development of a Tuning Technique for a Subsampling Bandpass Delta Sigma Modulator. It is highly relevant for the field of quantum computing. So, Jesko, you take to the stage. When the clock runs, 3 minutes, start.
So hello, my name is Jesko Fleming and I'm going to present my master thesis, which is part of the fast-track PhD program at the Hannover School for Nanotechnology. Today's quantum computers use very cold temperatures, so cryogenic temperatures, to hold the fragile quantum information stable. These qubits are read out and manipulated through room temperature electronics, which need to be connected down this cryostat. To solve practical challenges, however, we need to scale up the number of qubits, as said before, and increasing the numbers of these cables running down this cryostat will soon be limited by the physical space inside it. So it is mandatory to shift the electronics from the room temperature closer to the temperature regime of our qubit samples. Such a scalable quantum computer will have a tremendous impact on our society, especially in the fields of mathematics and simulation, such as cryptography, optimization, forecasting, and drug development. Quantum computers will have a tremendous impact to solve tremendous challenges with our limited resources. In my master thesis, I present a system design of a so-called analog to digital converter to read out these qubits at these cryogenic states. When reading a qubit, it collapses to two distinct states, either 0 or 1, which can be translated into a reflecting or absorbing behavior for a microwave, which again is analyzed through such an analog to digital converter. My proposed system is designed to enable future scalability and while being efficient at these cryogenic temperatures, while being stable against the cryogenic effects which happen at the circuits due to the so-called delta sigma structure. Such a delta sigma modulator is shortly also called a noise sampling oversampling converter. So it's for one output sample, it samples the input multiple times, so oversampled, and the noise of the quantizer is shaped, so noise shaping. And in the exemplary output spectrum on the right, you can see that the distance between the blue signal component and the green noise floor is increased in that specific frequency band. This means that with this circuit, we can analyze and get further and new insight on the qubit behavior, and thus is a key part of future electronics for the readout of quantum bits at these cryogenic temperatures. Thank you for your attention.
Thank you, Jesko Fleming. Perfect. Thank you so much. So that was the third pitch, which means we now come to our fourth finalist, Maximilian Hollendonner. He completed his master's degree at Friedrich-Alexander-Universität Erlangen-Nuremberg. His thesis is entitled Sensing of Electrolytes with Nitrogen Vacancy Centers and Diamond. It's highly relevant for the field of quantum sensing. Maximilian, please take to the stage. As soon as the clock runs, off you go.
Thank you very much for the introduction and hello to everyone. As we all know, one of the most urgent challenges is how to stop global warming. Hereby, it will be necessary to replace fossil fuels by green energy sources, which can then be used by electric vehicles. But electric vehicles, they require high-performance batteries. And therefore, there is quite a high demand in these kind of batteries at the moment. To satisfy these demands in an environmental friendly fashion, we need batteries which are long-living and therefore safe resources. This is often not the case for today's batteries, because one observes that with increasing cell age, the performance degrades and, for example, the capacity of the battery is decreased. What one could do would be to use a smart battery management system. Such a system would consist of a smart controller, which controls the operation parameters of the battery, plus a sensor. But as degradation happens due to effects at a molecular level, we need to have a sensor which can detect these effects, in particular, which can sense ionic concentrations. And up to now, there exists no sensor which can do this with the required spatial and temporal resolution. In my master thesis, I investigated whether a nanodiamond, which would be mixed into the liquid electrolyte of the battery, could serve as such a sensor. How does this work more in detail? To serve as a quantum sensor, the nanodiamond needs to contain a so-called envy center, as we've heard before. An envy center, that's a vacancy, so a missing atom next to a nitrogen atom. The ions inside the electrolyte of the battery, they generate radial electric fields, and these fields, they influence the ground state, spin state of the envy center. By analyzing how the electric field components act on these spin states more in detail, we found a way to extract them through repeated microwave pulse sequences. What is this then good for? Well, besides being able to measure electric field fluctuations, we can also measure the electric field fluctuations. From simulations, we found out that there's a direct relationship between these field fluctuations and the ionic concentration, which therefore means the nanodiamond can indeed be used as a concentration sensor. And this is then a starting point to measure and understand degradation inside a battery more in detail. We can, on the one hand side, optimize the battery such that degradation is attenuated, but we can also monitor the degradation in situ and in operando, so while the battery is being operated. If this is then fed into a smart battery management system, we hope that this will contribute to produce long-living batteries. Thank you for your attention.
Thank you very much, Maximilian. And pitch number 4. And now we come to our 5th and last finalist in the master's category, Janis Wagner. He completed his master's degree at Johannes Gutenberg University in Mainz. His thesis is entitled Automated Generation of Shuttling Schedules for a Scalable Trapped Ion Quantum Processor, and that is highly relevant for the field of quantum computing. Janis, please come to the stage, grab the microphone, and as soon as the clock starts, off you go.
So welcome to my pitch about automated generation of shuttling schedules for a scalable trapped ion quantum processor. As the title suggests, it addresses segmented ion traps, as can be seen over here. So different segments, which are Paul traps, store a few ions each. And with dedicated voltage control, we are able to translate ions, separate and merge, and swap ion crystals, and with laser control we manipulate the ion states. This is a picture of the currently operating chip in the Quantum AG Schmidt-Kahler at the University of Mainz, as well as the level scheme of the calcium-40 ions, which we're using as qubits. So the purpose of my thesis is to compile a quantum circuit, as can be seen over here, into a shuttling schedule. So a shuttling schedule is basically a list of operations which can be performed on a certain hardware and allow the performance of a given quantum circuit. So what one can possibly see is that the ordering of the ions in the shuttling schedule differs from the ordering in the quantum circuit. and that the ordering of the physical ions need to be changed over time. So what I possibly forgot is this on the x-axis you can see the different segments. On the y-axis shows the time evolution of the ions. Here you can see the laser control that needs to be applied. So both problem, the initial mapping as well as the reordering, are NP hard, and that's why I needed to provide a heuristical approach to solve them. With the provided system, I was able to evaluate the shuttling overhead with respect to gates and qubits, and to adapt the possibilities of a trap to also make the translations linear. By allowing separation and merge, so the operation seen over there, on every segment. Another major topic is the analysis with respect to the trap size, since the compilation is architecture aware. And this allows for the planning of trap sizes with respect to certain circuit sizes. All this can be done in only seconds of runtime due to the heuristic approaches I took. At last, I would like to promote 2 papers where were contributed. Both can be seen over here. Thank you very much for your attention.
Thank you, Yanis. And that was the 5th of 5 master's thesis presentations, pitches. So for everyone online, just take a breather, run quickly through the list. Just remind yourself, these are the ones that you favored, because now we need your full concentration for the next round of finalists when it comes to the PhD or doctor's thesis category. Again, we have 5 finalists. Again, they have 3 minutes for their pitch. We're starting with Dr. Matthias Bock. He completed his doctorate at the Universität des Saarlandes. His thesis is entitled Polarization Preserving Quantum Frequency Conversion for Trapped Atom-Based Quantum Networks, and that's highly relevant for the field of quantum communication. Matthias, you're ready to start. Please take the stage, grab the mic. 3 minutes, start now.
All right, good afternoon from my side, and thanks a lot for the opportunity to present research from my PhD, which I did at Saarland University in the crew of Christoph Becher. And our big vision, let's say, is the implementation of a quantum network or quantum internet. And you see in the upper left such a nice schematic. Such a network consists like a classical network of nodes where you store or process quantum information. And these nodes are interconnected by channels where we distribute that information between the nodes by means of using photons, so the quanta of light. And the big goal of this is actually to create special non-classical quantum mechanical states between remote nodes. In our case, these are entangled states. And what is the advantage? As soon as you have these entangled states, you can use them as a resource for some very exciting applications. Among them, the connection of quantum computers, ultra-secure communication, or also some more fundamental topic like you can use this to improve the performance of optical clocks. And actually my thesis was exactly about realizing one link here consisting of 2 atomic nodes over long distance. And what is the challenge there? Well, you can ask the question, how do you implement these quantum channels? And we would like to use optical fibers because there's already a super nice fiber infrastructure. You see here these undersea cables, which for instance connect data centers in the US or Europe. So we really should hope that these cables are hidden a bit better than the Nord Stream pipelines, because this is actually the backbone of our global internet. And now one major problem is if you look at the transmission, so you have losses, and these losses of the photons strongly depend on the wavelength. For instance, at 54 nanometer, this is a wavelength given by our atomic quantum nodes. You see here this number, this does not look really promising. And even if a PhD thesis can take several years, right, with this number, it's pretty much hopeless. This transmission is just too low. But what is very nice is if you go to the so-called telecom C-band at 1550 nanometers, so a different color, you have a much better transmission. So you can either now look, okay, do I find quantum nodes which operate the telecom wavelength? And as a funny coincidence, we will hear about this in a subsequent talk. But what we do is, our solution is here to use quantum frequency conversion, which is an optical device here. You see it down here, where we send in single photons at 854 nanometer, for instance, convert them to telecom band at 1550 nanometers. But all the other properties, so the entanglement, are preserved in this process, and simultaneously it works with a very nice efficiency. And this enabled, so we built several of these devices, and this enabled some exciting experiments. For instance, in collaboration with Jürgen Eschner, we were able to entangle a trapped ion with a telecom photon, travel through 20 kilometers of fiber. And the highlight experiment was together with Harald Weinfurter at the LMU Munich. So you see, this is a map of downtown Munich, where we had 2 trapped atom nodes, and we entangled them over 33 kilometers of fiber by means of quantum frequency conversion. Yeah, with this, I want to thank my group at Saarland University, group of Christoph Becher, but also our collaboration partners, Jürgen Eschner at Saarland University, Harald Weinfurter in Munich, and also you, live and online, for your attention. Thanks a lot.
Thank you. Thank you, Matthias, and thank you for being so generous to tease the next pitch already, which will be presented by Dr. Chiara Lindner. She completed her doctorate at Albert Ludwigs University in Freiburg. The title of her thesis is Nonlinear Interferometers based on spontaneous parametric down conversion for Fourier transform mid-infrared spectroscopy. If she doesn't stumble over that, then she's already a favorite of mine. It's highly relevant for the field of spectroscopy based on quantum mechanical effects. Chiara, please take to the stage, grab the mic. 3 minutes are about to start.
Okay, well, thank you. Hello and welcome to my talk. Well, when people hear about light, most people only think about visible light. But light is so much more. For example, infrared contains valuable information. Most molecules absorb at very specific and characteristic infrared frequencies. And if we analyze those by infrared spectroscopy, we can determine the structure and composition of many samples very precisely. This is important in many fields of industry and science. However, there is a tiny problem. For infrared light, we of course need infrared detectors. And like our eyes, detectors work best at the visible spectral range. So ideally, we would like to detect visible light, but get the infrared information. And well, quantum can help us do just that. And here is how. We can use a special quantum light source, which always emits 2 photons. One infrared, which we'll send to a sample, and one visible, which we'll send to a detector. Now, we'll then use a second identical light source. And if the sample doesn't absorb, we will see interference for both the visible and infrared light. Now, here's a special quantum effect. If the sample absorbs, we see either such a correlated light source. It can only show interference either for both infrared and visible light or for neither. So if the sample absorbs, we see no interference for the infrared, but also for the visible light. And we'll then turn this around. In our experiment, we'll just measure the visible light interference, and from this we can determine the infrared transmission without any infrared detection. So this sounds nice and all, but how do we get an actual infrared spectrum? Well, this is what I did in my PhD. I did 2 things. First off, I used a very broadband quantum light source. And secondly, I found out that we can use this interference itself, not only for the amplitude information, but also to get the wavelength. The expert would know this as Fourier transform analysis. But this way, we can get very broadband frequency spectra with a very good resolution, good accuracy. And me and my colleagues, we turned this into an actual device, our quantum Fourier transform spectrometer. With this, we can actually measure the fine absorption lines of molecules in the infrared using only visible light detection. So I hope that I've shown you and convinced you that we can use quantum technology to see and to measure better in the infrared. Thank you.
Thank you so much. I know this is the trickiest part of the pitch, putting the microphone safely back on the table. Thank you so much. We're moving on now to the 3rd finalist in this PhD thesis category, and that is Dr. Benjamin Merkel, who completed his doctorate at Technische University in Munich. His thesis is entitled Enhancing the Emission and Coherence of Erbium Dopants. and that is highly relevant for the field of quantum networks. Benjamin, you're ready to go. Grab your mic, 3 minutes, start now.
Thank you. Many quantum devices struggle to make relevant impact on industrial applications, typically because of their limited size. A quantum computer that controls only 4 qubits, for example, could never compete with its classical counterparts. Unfortunately, scaling up to more qubits is difficult. This is where quantum networks come into play. By connecting 2 or more quantum computers of small size with quantum links, the resulting network would be the equivalent of a much larger and powerful quantum computer. Such quantum links could be implemented by photons traveling through optical fibers and would also provide means of quantum secure communication. Eventually, these links would be the foundation of what we like to call the quantum internet. As building blocks for such a large-scale quantum network, we propose erbium-doped crystals. First, because they operate at a telecom wavelength with the lowest possible loss in optical fibers, which is necessary for large distance links. This property is already utilized by the classical internet, which operates exactly at the same telecom wavelength that is compatible with erbium-doped devices, which means we can build our systems on top of technology and infrastructure that already exists. Then this platform is a solid-state system, which leads to a very simple setup. You just need the crystal with the erbium dopants, the cryostart for cooling, and a laser for optical control and readout. And last, erbium-doped crystals can store quantum states. In my PhD, I demonstrated coherent control of electronic spin states and analyzed the possible storage times. You can increase the storage time a bit using special control sequences called dynamical decoupling, but ultimately you're limited by ensemble interactions. To increase the coherence times further, you'd have to go to lower dopant densities, which comes at the price of much weaker optical signal. Therefore, I also built an optical resonator to increase the coupling efficiency to light. By putting the crystal between 2 mirrors, the light basically bounces back and forth and interacts with the crystal 100,000 times, which boosts the efficiency of this quantum device. Such high fidelity requires stabilization of the mirror separation on a picometer scale, which was a technical challenge. Erbium-doped crystals have another advantage when it comes to scalability for industrial applications, and that is their great multiplexing capability. In a single device, in a single resonator, there are thousands of dopants coupled to the light field, and all of them have their own optical transition frequencies. In this spectrum, you see many emission lines, and each emission line corresponds to one erbium dopant that we can address individually and use as a separate quantum storage system. To sum it up, quantum networks can solve the long-standing scalability problem of many quantum devices. Erbium-doped crystals are ideal building blocks because they're compatible with existing technologies, they're relatively simple to install, and they provide great multiplexing capabilities out of the box. The biggest technical challenge was the incorporation into high-finesse optical resonators at low temperature, and that's what I have achieved in my PhD.
Thank you. Thank you, Benjamin. Thank you so much. So we have 2 more finalists in this category. The 4th one is Dr. Dominik Niemitz. He completed his doctorate at Technische University in München. In his thesis, his thesis rather, is entitled Non-Destructive Detection of Photonic Qubits with Single Atoms in Crossed Fiber Cavities. Fiber or fibber? Fiber. Yeah. Typo. Fiber cavities. And that is highly relevant for the field of quantum communication. And I'm sure you're doing a great job now. Please take to the stage, grab the mic, and the 3 minutes are about to start.
Yeah, first of all, I want to thank the organizer for having me. It's really an honor to be here. So I want to talk about light. Light plays a very important role in our everyday's life. For example, in communication, where light is used to carry information from one place to another at the speed of light. And due to this high speed, one can establish rather high communication rates at even large distances. So what is communicated? Typically zeros and ones that can be represented by the 2 sides of a coin. But light can do more. It can also encode quantum information that does not consist only of 2 states, but of infinite states that can be represented by a spherical sphere. So due to this, light can be used to establish remote entanglement or remote quantum computation and many more applications. But there is a fundamental problem in this photonic quantum world. There is light gets easily lost when flying from one place to another. And so in usual communication, this communication one have distances of for example, of 600 kilometers, which is here the distance between Munich and Berlin. One can imagine that this loss of information is a severe problem for the quantum computation. So what to do? One can, for example, place a detector along the transmission channels where the detector detects the presence of a photonic qubit which is flying by. And if it's lost, the detector can tell the sender to re-emit a photonic qubit, and if it's present, the photonic qubit just can just continue to the receiver's location. And by this approach, the communication rate can be enhanced as the potential photonic loss is detected already at an early stage. So in the frame of this work, such a non-destructive detector has been experimentally demonstrated for the very first time by using crossed optical fiber cavities, as you can see them here, that are both coupling to a single rubidium-87 atom. So despite the fact that this demonstration has still space for improvement, it shows a performance that is still good enough to be used for some of the nowadays known quantum communication protocols. So this detector is a very promising future quantum technology that mitigates the effect of fundamental photonic losses. Thank you very much.
Thank you. Thank you, Dominic. I know, just give it to me. Just is the easiest way. So we have one more finalist, and his name is Dr. Kirill Spasipko. He completed his doctorate at Friedrich-Alexander University in Erlangen-Nuremberg, together with Max Planck Institute for the Science of Light. His thesis is entitled Spectral and Statistical Properties of High-Gain Parametric Down Conversion, and that's highly relevant for various fields of quantum technologies. Kirill, welcome. Take to the stage. Here's your microphone, and the 3 minutes are about to start.
Thank you very much for the introduction and for the opportunity to present my work here. My PhD work was related with parametric down conversion. You already heard about it, a couple of talks before. And this process occurs in nonlinear crystals with the subspacial crystals, and in this process, each high energetic photon called pump, it converts to two daughter photons, signal Adler. And these two daughter photons were actually entangled. And basically, the spontaneous parameter down conversion, it's actually the easiest way to get entangled photons before you have already seen it at a couple of talks. But unfortunately, this spontaneous case, where you get only two photons, it has only low powers. Usually it lies something about in picowatt or nanowatt power range. Before it's suitable for quantum applications, but not so suitable for consumer products. But however, one can get with PDC also very bright states, and this is so-called high-gain regime. In this regime, when we just pump more and more photons from a laser, get more and more intense pump, then we will get each time not two photons, but four, and more, so on and so on. And process efficiency scales exponentially. And actually, in the end, we get, instead of only two pair of entangled photon, we can get two bright entangled beam. And my PhD was basically related to this high-gain regime. And during my PhD, I have shown that one can get higher resolution for sensing and imaging, enhanced multi-photon effects using high-gain parametric conversion. But the key point I would like to emphasize right now, that it has actually milliwatts of power, like a laser. For example, here below you can see signal Adler beams just on a piece of paper. It's exactly as bright as a laser, and therefore it's suitable for consumer products. And this is what, and actually, to go to high-gain regime, we can enhance the pump power, but the lasers are quite bulky and expensive. And we can go their way. And what is I'm doing after my PhD at Quant? So we are developing the high-gain parametric down conversion in nonlinear waveguides. In a linear waveguide, the light remains tightly focused over long distance. And before we can get to high-gain regime, even with cheap laser diodes. And this is basically our vision in this project. So we are developing waveguides, packing everything together, and would like to improve the consumer products that use a laser for projection imaging using high gain parameter and down conversion. And as a last, I would like to say that all these nice things we talk today will be impossible if we don't stop crazy dictators that could destroy our world. So stop Putin and support Ukraine. Thank you. They're fighting for us.
Thank you, Kirill. Thank you, Kirill, also for having the nerve to come up with that statement towards the end of your pitch. And if I just may add, we gave everyone 3 minutes, and we all said that's very short. I think for the next Quantum Future Awards, we can even reduce the time to 2.5, because that was pretty much the average time that all of you took. Well, ladies and gentlemen, we had 5 fantastic presentations, the master thesis. We had 5 fantastic PhD thesis presentations. And I personally don't envy you, because you have to make a decision now, the jury in particular, but also you out there, and I hope you did take my advice and you took notes throughout the presentations, so you can remember which of the pitches you favor. We have 10 minutes, a break now, in which you can reflect on the pitches and the jury too. After those 10 minutes, the jury will return to share with us their decision, and we will also find out about the public vote, the one that you voted for. So do make use of the time, 10 minutes from now, and of course I keep my fingers crossed for everybody. See you in a bit. Welcome back. The public voting has ended, and also the jury members are back here in the room with us, because it is now time to find out who the winners and the runners-up are of the Quantum Future Awards 2022. And we start with the runners-up in both categories, namely Masters and PhD. And for that, I already have two of the jury members with me here on stage, Dr. Michael Marthaler and Professor Dr. Christiane Koch. And I believe, Dr. Marthaler, you'll be the one to announce the runner-up in the Masters category, yes. And why?
Yeah, thank you.
And this microphone doesn't seem to be
It's not on.
now.
Thanks.
Good.
Yes. So I'm very happy to announce the runner-up in the category for master thesis, and it's a great topic to work on quantum sensing, especially in the life science. I feel this could be really incredibly useful, and so I'm happy to announce runner-up is Robin Allard.
Congratulations, Robin. Please join Dr. Marthaler. Do stay with us. Not so shy. Not so shy. Do join him. So, Professor Koch.
And we have the runners-up in the PhD category, who is Kirill Spasibko. Please come to the stage. We really appreciated the breadth of results, which was a nice mix of fundamental science with application potential. So congratulations.
Thank you very much.
So, Kirill, also please do stay with us. So we have the runner-ups in the Masters and the PhD category. And I can just share with everybody outside that all the scientists who were presenting their pitches during this short break were gobbling down liters of water because all the tension finally subsided. And our third jury member, of course, representing politics in this case, Professor Schiefer-Decker, you're going to announce now the winner in both the master and the PhD category. Very, very curious.
Yeah, thank you so much. Before we do announce the winners, I want to repeat, all of you are winners today. All of you won your excellent master and PhD thesis. So please continue and take on your scientific journey and your professional career, no matter what you choose in science or industry. But please go on, no matter who we're going to announce now. So, but anyway, last year I think I attended a demonstration in Bonn between the BMBF and the BSI. Mr. Chandrasekhara, I'm very pleased to announce you as the winner at the master. So I hope I'm not, no.
And picking the right one?
Yes, picking the right one. I don't need the mic, by the way.
Nope.
Congratulations.
Thank
very
you.
well done.
Thank you very much.
Good luck further on.
So, and please also stay. We have a big collection at the end here on stage.
And I'm also pleased to announce now the first place with the PhD students. But before that, I wanted to tell all the master students that you really mastered your pitches. We were very, very much impressed because we had so much, not only pace, engagement, everything, but so they say you stood there on your own and you come over with your messages and your content and your results. Very well done. So now to the PhD students, of course, they have very in-depth thesis developed, and here I'm very pleased, Chiara, that the prize goes to you. Congratulations for the spectacular. Wrong.
Thank you.
Excellent.
Thank you.
Good luck.
Congratulations to everybody. And of course, we still have one award to bestow. And for that, I just step in the middle because that I can read the screen better. I can read the screen better because you were asked to vote. Who convinced you the most? And maybe it's one of them already on stage with us. Maybe it is someone else who is still waiting to get an award and a prize. So let's find out who you voted for. Can we please have a look at the result? Do we have the result? Yes, we have the result, and it's right behind me. And the winner, the public vote winner, is Uday Chandrasekhara. So, double. Followed by Chiara Lindner, Jessica Fleming, and Maximilian Hollendonner. You've also popped up in the public vote. So congratulations to all of you. And this basically brings this Quantum Future Award ceremony 2022 to an end already. But looking at the faces of our young scientists, I know that this is just the beginning. The work continues. We know certainly that quantum technology, quantum mechanics, quantum communication, and all those different fields, they will play a big role in years to come. So we will need your input, we will need your expertise and your hard work. So continue the work, because the next Quantum Future Awards, 2022 is coming to an end, but 2023 is just around the corner, and I'm sure we will have some fantastic projects there too. So thank you very much, everyone, for being here, our young scientists, our small but very illustrious audience here in the room. A big, big thank you, of course, also to our jury members and our host in particular. A thank you that I was allowed to be here with you this afternoon. And stay safe, stay healthy, and keep up the good work. And Uday wants to say something, but for that you will need a microphone.
Thank you. Yeah, if I take the credit of this work myself, I think I would fail immediately, and I wouldn't get a better opportunity to thank other people how much they helped me throughout my academic career. My professors, supervisors, my friend and family, they both are same for me, and they're cheering me now. Looking all over the world, they have been voting for me. I thank everyone once again. And a small appreciation for myself. I do feel this is a very good start for me. Thank you very much.
Thank you, Uday. Thank you. And as you know, and as you can notice, that wasn't planned, but that was a very good move, which is why I would like to just turn around anyone else who would like to thank anyone, because now is the time. Kirill.
I would like to thank my professor, Maria Chekova, my family who is here, and everybody at Quant who is supporting me. We would like, let's define photonic future with light.
Yes, so I also want to thank Dominic Bucher, my professor, who has taught me so much over the last couple of years. I want to thank all my friends and fellow students in the group, and I want to thank my family and, of course, my girlfriend who is here.
Wonderful. We have one more. Chiara.
Thank you for the opportunity. I wasn't counting on it. First of all, I'd like to thank my supervisor, Frank Kühnemann, and all at the Institute for Physical Measurement Techniques, the Fraunhofer IPM at Freiburg. They helped me, they supported me throughout my thesis, and it wouldn't have been possible without them. And of course, friends and family always help and support and bring us through this time of PhD or master theses. Thank you.
Thank you. And with these closing words from the winners themselves, let me say thank you and goodbye.
Thanks. Und natürlich darf ich Ihnen